All right, Chapter 7 then. Chapter 7 is going to build on what we've been doing in Chapter 6, as we've been doing stuff, as we've been working with finding that area between and using our z-scores. Now we're going to be taking that a step further as we do things. So kind of backing up and going through what we've already talked about so far. Chapters 2 and 3, we use the descriptive statistics when we summarize data using tools such as graphs and statistics such as the mean and standard deviation. So starting off with, we looked at the statistics of our test score and what we were able to look at as far as the mean, the standard deviation, the different quartiles to kind of describe how you guys did on your test. We could have, probably wouldn't have made a lot of sense to have done it, but we could have made like a bar graph where you showed how many A's, B's, C's, D's, F's type of thing that we had on those to be able to describe what that data looked like. And we would have noticed on this data for sure that we had a skewed data set. It wasn't going to have that nice normal distribution because we definitely had a lot of people that did real well on the test. So using that, and that's what we've talked about so far in Chapters 2 and 3. Chapter 6, we introduced the z-scores and the normal distributions. So that's what we just came from, was using those z-scores and having something that came from a normal distribution to try to figure out the probability of that value happening. Where we're going in this chapter. This chapter begins inferential statistics. The two major activities of inferential statistics are to use the sample data to estimate values of population parameters and to test hypotheses or claims made about population parameters. So when you're looking at inferential statistics, you're taking the group that you have, this little sample that you have, to try to do something to describe what's going on with the entire population. Whether it's the fact that maybe I know the mean ages of a small sample of NCMC students, and I'm trying to use that to try to infer what I think the average age of an NCMC student is, the entire population. Or maybe I might make a claim that I think the average age of students is more than 20. Well, if that's my claim, then we can use our sample to try to infer, to test that hypothesis, to test that claim of what I think is true or not. So those are the two major things that we're going to be looking at. So Chapter 7 focuses in on using the sample data to estimate the values of the population parameters. Chapter 8 is going to look at testing the hypotheses. So both of these are going to be main places that we're heading towards. We're going to introduce methods for estimating values of these important population parameters. We're going to look at estimating the proportion, the mean, and the variances. We also present methods for determining sample sizes necessary to estimate those parameters, which is going to be deciding how big that sample size, how big N needs to be able to have a large enough sample to do anything with it. Questions about the general direction of where we're heading? So these last two things, what was on this slide, those are what we're aiming for on this chapter. We're going to start off making sure we understand a lot of the basics and spending a lot of time figuring out how to estimate the population parameter of proportion. What you're going to do for proportion is going to be the same concept for doing the means and the variances, and whether we have the mean when we know the population standard deviation or if we don't know the population standard deviation. And the process that we go through is very similar for all of them. The tests and the actual calculations of the data will look different for each one of them. All right, so starting off with, on this one, estimating the population proportion. Before we even start, looking at an example of what we're talking about doing. If this is the percent of people with a bachelor's degree or higher, population 25 years of age and over. And so it's got looking at those. Well, if we come down here to Missouri, then it's giving me the percent that were in my sample. So in my sample, there's 23.9% of the people ages 25 and over that had a bachelor's degree or higher. But then Just because that sample had 23.9% does not mean the true population of all of Missouri, that it's right at the 23.9% of them have their bachelor's degree or higher. This is what we call that confidence interval. The true value of the population, and this would be a proportion, is going to be between 22.6 and 25.2%. You don't know from a sample, you can't say, well, it has to be exactly this. But we can be pretty confident that we're going to capture what that true mean is, what that true population proportion is. That it's going to be somewhere between these two values. And this one is having a 90% confidence interval. So I'm 90% confident based off their what they've done. They're saying they're 90% confident that the true population proportion of Missourians that have their bachelor's degree is between 22.6 and 25.2%. So these are things that you see in papers and in a lot of different kinds of journals, especially if it's anything that they've done any kind of research. They usually give those kinds of things out. Another one that you see a lot is if you talk about presidential election polls. You know, whenever presidential elections or any kind of elections coming up, they're going to say, 52% of people support whatever candidate at the time. But then they always have this plus or minus 2%. They always have that plus or minus margin of error, because just because they've sampled it doesn't mean that they're going to be spot on what it is. So having that 52% plus or minus 2% might mean it's up to 54%. It might mean it's down to 50%. But it's somewhere in that range is the true population proportion. I'll figure out if I'm going to show this one. This one's looking at showing things graphically, where it's got this margin of error, where it's giving me a 95% confidence interval, and it's giving me with those 4% more or less, as we're looking about rounding around that 48% estimate. So they're giving you what that lower and upper bounds are. They've even included that in their shading, that they think it's somewhere in that range. And that one's coming from voting. So lots of different things as you're talking about doing these, that they have a lot of applications to them. All right. Key concept in this chapter then, or in this particular section. The sample proportion is the best point estimate of the population proportion. We've already looked at that. We looked at the fact that if I was to take every single sample of the same size, sorry, skipped a page, I want to make sure I had there. When we were looking at every single sample of the same size, and we took every single one, so when we were talking about, and it took me a while to get it figured out, but when I was looking at those numbers 1 through 3, and every sample of size 2 numbers, that when we took the proportion of ones, that the best estimate of the population proportion was that sample proportion. And we could take the mean of the sample means was going to be the population mean. Well, it's taking that idea and just building on it, that we can figure out the best estimate we can have for the true population proportion is our sample proportion. We can use a sample proportion then to construct a confidence interval to estimate the true value of a population proportion. We should know how to interpret such confidence intervals. So we're going to be figuring out what is that range of values. What should be my plus or minus how many percent as we're doing things. We should also know how to find the sample size necessary to estimate a population proportion. So these are the key main ideas that we're going to be covering in just this section. And as I said, we're going to cover them pretty thoroughly in section 2 when we talk about population, or when we talk about proportions. But then we're going to use the same ideas when we're talking about the mean and the variance. So, first of all, the definition. The sample proportion P hat is the best point estimate of the population proportion P. Keep track of your notation. Lowercase p is talking about it being the population proportion. P hat is when we're talking about the sample proportion. And so if I was to find a sample of, let's go with a sample of cars. We went out to the parking lot and we'd use them as a sample of cars, and we counted how many red cars were in the parking lot. And we figured out that there were 20 red cars out of the 52 cars that were out there. Oh, let's make it easier. Let's do 20 out of 60. if I went out there to the parking lot, I found there was 20 red cars out of the 60 cars that were out there, then the sample proportion, the p hat, would be the 1/3. That 1/3 of the cars out in our parking lot were red. Well, that would be my sample proportion. My best estimate, if this was a good sample that we were using, the best estimate then of cars in Trenton would be that 1/3 of them are red. Now, it's not going to be that it's exactly 1/3 of them that are red. It might be a little above, it might be a little below, and that's what we're trying to figure out is how far off could we be? What is that range of values we would need to have as we're going to do that? Part of that will depend upon our sample size. Now, one key thing is we have to make sure we have a good simple random sample. My parking lot may or may not be a good sample. Might not be too bad of one. Because I don't know that there'd be anything about being a student that would really influence your color of car choice. So it might be a decent sample to be able to use. So our confidence interval then, or interval estimate, is a range or an interval of values used to estimate the true value of the population parameter. A confidence interval is sometimes abbreviated as the CI. So you'll see us using that quite a bit as we talk about that confidence interval. What is that range of values? My sample proportion should be within that confidence interval. But how big does it need to be? If I'm saying that, my sample is 1/3 of them are red, how wide around that do I need to have to be able to truly make sure I'm catching the true population parameter? The confidence level is important. That confidence level is the probability with that 1 minus alpha, often expressed as the equivalent percentage value, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. Most often, the ones we're going to talk about, that one I talked about with our Missouri people with bachelor's degrees, was that 90% confidence level. If it's a 90% confidence level, that means alpha is 10%. Because your probability level is the 1 minus alpha when we're looking at this. So I'm going to be they were 90% confident that the number of people with bachelor's degree was between whatever those two numbers were. Frequently, we'll use 95. 95% confident is the one that you see the most often. If you really want to have a very high confidence level, they'll use a 99% confidence level. So depending upon how confident that I want to be that I'm truly capturing the true parameter will determine what that level what that alpha value will be. So if I'm at 99%, then alpha is the 1%. If I'm at 95% confident, then the alpha is the 5%. Questions on any of the notation so far? If the confidence level is 95%, then what we will say is, I am 95% confident that I have trapped the true proportion in this given interval. So that's the way we would word what we have found. So that's the reason why when I was looking at the one with the number of people with the BS degrees. So if we went with the highest value that we had, which was Massachusetts. So ignoring the District of Columbia, if we went with Massachusetts, they're saying their sample had 35 point. Well, I can actually just go with the United States. Let's go to the very top one. With that United States, their sample proportion was the 25.9. They're saying the true values are somewhere between 25.6 and 26.2. So they are 90% confident that the true population parameter of citizens that are over 25 that have a bachelor's degree is between 25.6 and 26.2%. So there's that 10% chance that it might be outside of those values. There is still a chance that it might have a 26.5% being the true population parameter. It may be a little below the 25.6, but more than likely, 90% chance that it's actually going to be between the 25.6 and the 26.2. Without testing every single person in the population, you can never be 100% sure that you've got the true proportion within your range. as we're doing things. Now, if you went to doing the census, and if they included, and I think it is on the census of what is the highest degree of people within the home, might be how they actually word it. I don't know if they do it for every single individual, if it's just for somebody within the house. But I know there's something in there about education. So if that was on the census, and so then they did take it from every single individual inside the United States, then they can say the actual true percent is, and they can give you whatever that number was from that. It wouldn't be from a sample, because it would be a parameter from that population, because they would know every single value. Otherwise, most of the time what we're going to be saying is, I'm just this confident. And so that in this problem that we were just looking at, alpha was the 10%, versus most of the time we're going to be using that alpha being the 5%. All right, what we have to find then, we have to find our critical values. A standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are unlikely to occur. Such a z-score is called our critical value. For instance, if I'm wanting to be 90% confident, then that's telling me my 10% is what's out there of being unlikely. And it depends upon how we're, I guess all of these will be two-tailed tests. So that's telling me between the two ends that 10% is what's floating out there. I could be a little lower or I could be a little higher than that. So 5% in each tail would be what we'd be looking for. So what would be those z-scores that would cut off the 5% on each of those two tails if you're wanting to be 90% confident? And so those are your critical values, those pieces that cut off what's likely to occur to what's not likely to occur. So trying to find those critical values. So under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. So most of the time we will be using that normal distribution if we meet certain certain things. The sampling. So then when we look at doing this, if we're wanting to be that 90% confident, then that means alpha is the 10%. And as I was just saying a second ago, that means between those two tails, we can have that 5% in each tail. And finding that z-score that cuts off that 5% in each tail. So this is your alpha over 2 would be the 5%. And over here, the alpha over 2 would be the 5%. Now, if I changed my confidence level, instead of being 90% confident, if I wanted to be 95% confident. Well, if I'm 95% confident, then alpha is only the 5%, which means I have 2.5% in each tail, which would be the same as saying 0.025 as my probability. So this would have my 2.5% in this tail. So you're just taking that alpha and cutting it in half because it's always going to be those two-tailed tests. You can have, or not tests, but two-tailed possibilities. You can have stuff below or above when you're talking about doing this range of values, your confidence level or confidence interval. Questions so far? Well, then let's find some of our critical values. To find them then, a z-score associated with a sample proportion has a probability of alpha over 2 of falling in your right tail. So we're cutting that in half. The z-score separating the right tail region is commonly denoted by z of alpha over 2 and is referred to as a critical value because it's on the borderline separating the z-scores from proportions that are likely to occur from those that are unlikely to occur. Notice it is that right tail is kind of the one that we're going to focus on most of the time when we talk about these critical values. Even though we've got the two tails that we're testing, we're cutting it into both pieces as we do it. So the one we're going to use the most is looking for that z of alpha over 2, of finding that critical value. So if I find this for the 95% confidence level, okay, I do have my pictures. So if I'm wanting to find z of alpha over 2 for my 95% confidence level, if it's 95% confidence, what's alpha? Alpha is your 5%. If alpha is 5%, what's alpha over 2? We're going to have the 2.5%, or that 0.025 is going to be the ones that fall in both tails. If I want, ignore my numbers, I don't want those there yet. If I want the alpha over 2 to be in each one of these tails, so 2.5% in this tail, 2.5% in this tail, what is that z-score that cuts that piece off? So where would I find this z-score? Back to using our tables, same tables we've been using back in chapter 6 that we were doing before. So if we were to look back at our table, and hopefully this is becoming one of those numbers we've seen so many times that it's almost committed to memory by now. And probably before you're done with this chapter it will be. So trying to find the 0.975 in the body of your table, your 0.975 is in the body of our table because that's giving us the area to the right being the 0.025 is going to be your 1.96. Trying to get it to where you can see everything at once. There we go. So you got your 1.9 and then you got your 6 at the top. So that critical value is going to be your 1.96. Now, if the one on the right is the positive 1.96, then the one on the left is negative 1.96 because we have that symmetry. You could look it up in the table of where you have the 0.025 as the area to the left. You're going to see it's the negative 1.96. So when you have a 95% confidence level, you don't have to go through this process every single time because, like I said, we're going to see these numbers so much. These are going to be the critical values that we're going to use. So as soon as you know that you're doing a 95% confidence level, if it's a proportion, so that I'm using my z-scores, if we've met them, those things where we can say we're using the z-scores because we had a population that was normally distributed, then we'll use the 1.96 and the negative 1.96 as my two critical values. On the other hand, so the critical values are positive and negative 1.96. If I want to be 99% confident, if I'm 99% confident, then what is alpha? 1%. So what is alpha over 2? Okay, it's 0.5%, so it's 0.005, which means I want to have 0.005 as my area on this right tail. I want 0.005 as my area, my left tail. If I am finding z of alpha over 2, what number am I looking for in my table? What is the area to the left? If I want 0.005 on the right, what do I want on the left? 0.995. So I'm looking for having the area to the left being 0.995. So what is your z-score? You're doing, if it was 90, yeah. So what are you guys getting for 0.995? Okay. So that was one of those that's at the very bottom because it happens so often and we don't see that number too often, or it doesn't fall exactly in there. So my z, my critical value, I don't have it written down there. My critical value then is the 2.575, which means my other critical value is what? Negative 2.575. Is everybody finding that? Because finding these critical values is a huge step within what we're going to be doing. So we're going to have to use those as we do the rest of our calculation. Okay. Now I want you guys to do the 90% confidence. guys come up with? So you're looking for the 0.95. So what are you coming up with? It's not.
If you were doing the 90%, then your alpha is the 10%. But you got to cut that in half. So you're really looking for having 5% in the right tail, 5% in the left tail. So you're going to be looking for the 0.95 is what you're actually looking for here.
Yeah. Okay, so if we're having that 90% confident, then that means alpha is your 10%, which means alpha over 2 is the 5% that's going into each of these two tails, which means the area to the left of the 5% means we're looking for the 0.95 in our table, and we get what? Okay, so that's one of them that's there at the very bottom. So you have the 1.645 and the negative 1.645 are our two critical values that we're going to be comparing things to as we do it. That z of alpha over 2, which is the key one that we're going to use, is when we look at the positive side. Now, because a lot of you guys got very calculator dependent, how could I have used the calculator to have found this critical value of 1.645? Okay, I could have done the inverse norm. Inverse norm of what percent? I'm going to let you guys kind of think this through because you're just throwing out every number you can think of, and I'm not going to stop you at the moment you say yes. Huh? Okay, you guys came to a consensus. Good. 0.95. Because I want to find the z-score that cuts off that area being the alpha over 2, the 5% to the right compared to the 95% to the left. Do I need to put in the mean and the standard deviation? No, because this is your standard normal. We're still sticking with the mean of 0, the standard deviation of 1. And so we could have done that, and you should get the 1.645 as your critical value. Now, I'd rather you guys make sure you know how to use the tables, especially since these three that we just looked at, you're going to see a lot of, especially the 95% confident. The first one we did is the one you see the most often. But 90% confident and 99% confident are other ones that you'll see sometimes. Especially if you're looking at it being a kind of a hard science type of thing. If we're talking about medical, if you're talking about chemistry, biology, those types of things usually want to have pretty high confidence levels. If, on the other hand, you're dealing with a social science type experiment, if this is something that's dealing with psychology, sociology, sometimes their confidence levels are a little broader to be able to get a better range of what that proportion, if you're talking about the proportion of kindergartners that have, grow up that have such and such kind of disabilities or something. Sometimes when they try to look at making a relationship between things, they sometimes make those broader ranges for the social sciences. Confidence levels are a little lower. So it depends on the situation what we're looking at too. When data from a simple random sample are used to estimate a population proportion P, the margin of error E is the maximum likely difference with that probability of 1 minus alpha between the observed sample proportion P hat and the true value of the population proportion P. This is also called the maximum error of the estimate. This is how far do I think I'm off. So this E, this margin of error, is saying based on the fact that I want to be 95% confident, this is my sample size, this is what I've done, this is the maximum that I think I'm off by. Do I think I'm off by 2%? Do I think I'm off by 5%? What is that plus or minus value? What is the furthest away I could possibly be? So when we were looking at, going back and looking at this example that we already had, the margin of error is saying how far off do I think I was? Well, between 25.9 and 26.2, they think they're only off by 0.3%. And same thing going below, between the 25.9 and the 25.6. They think they're only off by 0.3%. So that's their margin of error. So they're pretty confident that it's going to be pretty tightly packed in there. They've got a really high sample size, it looks like, when they were doing this one. But that's telling you how far off do I think I am? How far from what the true sample proportion compared to what the maximum and the minimum values might actually be? How far away do I think the true population proportion, P, is from my sample proportion, P hat? That margin of error is what we need to find so we can figure out what that plus or minus is. Now to find my margin of error, how far off do I think I am? This is the formula we're going to use. Because we're thinking it's going to be coming from a population that's normally distributed, we're looking at our z-score, that critical value, which is going to be the positive z-score, the z of alpha over 2. So we're always looking at the right tail when we do this. Times the square root of my sample proportion times the proportion that was false divided by n. Now, when we think back to chapter 6, actually, I'll give you a second to write that down, then I'll let you think back to chapter 6. Q is if it's the opposite of p hat, so it's 1 minus p hat, so it's the proportion that's false. I'm not seeing what I was wanting to talk about, how I would get from one place to the next. Yeah, I'm not seeing anything that's saying what I really wanted. I'm trying to figure out if I want to try to explain where this came from, but I'm not seeing what the formula that I was wanting to compare it to, so I'm not even going to worry about showing you guys where it's coming from on this one. So this is going to give me my margin of error. This is going to give me that plus or minus part. So, looking at what my different formula or what my different things stand for, P, remember, is the population proportion. P hat is my sample proportion. N is the sample size. E is my margin of error. Z of alpha over 2 is the z-score separating the area of alpha over 2 in the right tail of the standard normal distribution. I don't know why I didn't put that Q hat is your 1 minus your P hat. It'd probably be the easiest way to think of it. That is that proportion that is false, proportion that's not true. Can't read my writing. There's what I need. All right. Confidence interval for estimating a population P. These are the things that have to be met first. First, we have to have that the sample is a simple random sample. So again, how we collect our data is always going to be very important. The conditions for the binomial distributions are satisfied. That is, there is a fixed number of trials. The trials are each independent. There are 2 categories of outcomes, and the probabilities remain constant for each trial. So even if I was talking about my red cars in the parking lot, it was still a binomial distribution. Well, I guess maybe not completely because there wasn't necessarily a fixed number of trials. If I was making sure that I was only going to count 60 cars in the parking lot or something like that, to where we kept a constant size of my trials. Each trial's independent, so if I picked 60 cars from our parking lot compared to 60 cars from some other place, and so I had them each being independent, there's two categories of outcomes as far as it's red or it's not red. And we would assume that the probability of red cars would remain constant no matter where that I would go within Trenton. And so as long as those things were satisfied, we also have to meet the fact that there is at least 5 successes and 5 failures. So if you were to be trying to figure out the proportion of pink cars in our parking lot, or the proportion of pink cars in Trenton, and we went out to our parking lot and there was only one pink car, which I don't even think you'll find one pink car in the parking lot. But if you had one pink car in the parking lot, then that's not going to be able to meet this to where we could use that. We have to have at least 5 successes and at least 5 failures. So these things have to be met before I can even try to look at making my confidence interval. Then we're going to be, once we've met those criteria, then you find your margin of error E, and that's going to tell me how far away I am from my sample proportion. So if I look at working through an example, a simple random survey of 1,200 residents of Trenton found that 400 had attended NCMC at some point in their life. Find the margin of error that corresponds to a confidence level of 99%. Now, first of all, totally made up the data. So don't feel like I'm anywhere near accurate on this. So now, knowing that this was made up data that we're going to pretend came from a good simple random sample, so have I met the criteria first? Did I have a simple random sample? We're pretending that's true. Was it a binomial distribution? Was there a fixed number of trials? I surveyed 1,200 people. Was each trial independent? When I asked the first person, did they influence whether the next person went to NCMC or not? Okay. Was there only 2 categories? You either attended or you didn't attend. Did the probabilities remain constant for each trial? There is an actual proportion of how many people in Trenton attended NCMC. So that would be true. Was there at least 5 successes and at least 5 failures? Okay, I had 400 successes, which means I had 800 failures. Now, what I want to do then is to find the margin of error that corresponds to a confidence level of 99%. So if I want to have a confidence level of 99%, first of all, what is alpha? 1%, which means alpha over 2 is 0.005. Which means what is my z of alpha over 2? That is your 2.575. That is, if I have my normal distribution, I only want to have 1% in my 2 tails, which means I have 0.5% in this tail and I have 0.5% in this tail. And so then 2.575 is the number I would be looking for. That would give me, my area to the left of this was the 0.995. So that 0.995 is what you're looking up in your table, which is one of those special numbers that's at the very bottom. So now my z of alpha over 2 is the 2.75. What is p hat? What was my sample proportion? What? It would be 1/3. Why am I getting 1/3? Okay, 400 over 1,200, which reduces down to 1/3. Which means what is q hat? Okay, because q hat is the opposite of that. That's the proportion of failures. So we have the proportion of successes, the proportions that not successes or failures. And so now we'd be putting those numbers in. So as you put it in, you're going to put in your 1/3 times your 2/3. Oh, and I forgot to ask, what is n? It's the sample size, which is your 1200. Now, as you substitute it in, you've got to make sure you put stuff into your calculator correctly. You're going to need a lot of parentheses in this problem. You can either put it in as one big entire problem at one time, or you could do what's underneath the radical first, take the square root of it, then take that times 2.575. Let me give you guys a moment to plug it in. Mm-hmm. The parentheses he's talking about is the fact that you have to have the 1200 under the square root. So that one, and I'm going to delete that one because it's not. Because you've got
that one right there where I got 2 in a row.
You need to delete. I deleted one of them when you had 2 in a row because you've got this parenthesis. No, you want these two because you've got this is opening around the 1/3. This one's opening around to make it 2/3. This is saying I'm taking the square root of what? It starts here, it ends here. So you had to have the 1200 under the square root. Because what you were doing was taking the square root of the top divided by the 1200. Instead of taking the square root of 1200 first, or dividing it by the 1200 first, then it's taking the square root. Because you're off by 100. I'm not sure why. So if you're putting it all into your calculator at one time, it can look like this one. Now you've got to be careful with your parentheses as you're doing that, because you've got to make sure that you're taking that square root. And I know some of your guys' calculators are newer and look a little different. But once you do the square root, it's the square root of all of that, the PQ over N. And so you've got to put the P in parentheses, the Q in parentheses, divided by the N. There has to be that first parenthesis after the square root has to be closed to make sure that we divide that 1200 is inside there. Now, you could have just done piece by piece, where you took the 1/3 times the 2/3, divide that by 1200, take the square root of that, take the square root of that answer, take that answer times 2.575, and you should still get that same answer of 0.035. So you can take it piece by piece by piece, or you can just put it on your calculator as one big process to do it. Now that tells me my margin of error. That tells me how far away from the true sample, tells me how far off the true population parameter might be from my sample proportion. What was my sample proportion? My sample proportion was the 1/3. And this is saying from that 1/3, I might be above it by 3.5%, or I might be below it by 3.5%. So my true values is that 1/3 plus or minus that 0.035. So 1/3 is the same as 0.3 repeating, plus or minus that 0.035. So tell me how far above or below it I could be. And we will finish that next time. I'm actually not going to give you guys any homework over the weekend because I want to wait until this. I don't know how these keep falling on Fridays. It's really accidental, but it's great. Yeah. So, yeah. So no homework this weekend.